NEC Article 225.30 addresses branch circuits or feeders for multiple occupancies or tenancies. This article necessitates the separation of circuits and feeders for different occupancies. However, it doesn't specifically mandate the separation of power and lighting panels. In the 1956 NEC, Article 384 covered lighting and power panel boards. This article explicitly required the separation of power and lighting panel boards in certain types of buildings, but it was removed from the NEC in 1965. Currently, the NEC does not explicitly require the separation of power and lighting panels. It's a common industry practice to do so for several reasons. Firstly, safety. Separating power and lighting circuits helps prevent unsafe conditions like overloading or electrical shock. Secondly, maintenance. Isolating lighting circuits makes it easier to perform maintenance and repairs without affecting the power supply. Thirdly, efficiency. Separating power and lighting circuits can help reduce energy consumption by allowing for more efficient control of lighting. Based on industry best practices and past NEC requirements, it is highly recommended to separate power and lighting circuits into separate panels in a large building facility. This enhances safety, facilitates maintenance, and improves electrical efficiency. When dealing with electrical systems, it is always recommended to consult the latest edition of the NEC and local electrical codes, as well as qualified electrical professionals to ensure that all installations are safe and compliant. Consider consulting a licensed electrical engineer for detailed design and adherence to code. The NEC, or National Electrical Code, is a widely adopted standard for the safe installation of electrical wiring and equipment in the United States. It is updated every 3 years to incorporate new technologies and safety practices. The NEC is not a law itself, but it is often adopted by state and local jurisdictions as law. This means that compliance with the NEC is legally required in many areas. The purpose of the NEC is to protect people and property from electrical hazards. It covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. The NEC is a complex document, and it is essential for anyone working with electrical systems to be familiar with its requirements. Several specific articles within the NEC are relevant to panel board installations and circuit separation. These articles provide guidance on how to properly install and protect electrical panels, as well as how to separate different types of circuits. NEC Article 408 addresses switchboards, switchgear, and panel boards. This article covers the installation and construction requirements for panel boards, including enclosure requirements, overcurrent protection, and grounding. It specifies the requirements for the physical installation of panel boards, ensuring they are properly mounted, supported, and accessible. It also covers the internal construction of panel boards, including busbar ratings, wiring practices, and component selection. NEC Article 210 discusses branch circuits. This article provides requirements for the installation of branch circuits, including conductor sizing, overcurrent protection, and grounding. It also covers the types of outlets and devices that are permitted on different types of branch circuits. It dictates the allowable ampacity of conductors based on their size and insulation type. It also specifies the type and rating of overcurrent protection devices required for branch circuits. NEC Article 215 covers feeders. This article provides requirements for the installation of feeders, including conductor sizing, overcurrent protection, and voltage drop. Feeders are the conductors that supply power from the service entrance to a panel board or other distribution point. Article 215 ensures that feeders are adequately sized to carry the intended load and are protected against overcurrent. It also addresses voltage drop to ensure that the voltage of the panel board is within acceptable limits. NEC Article 230 addresses services. This article provides requirements for the installation of service conductors, including conductor sizing, overcurrent protection, and grounding. The service is the connection between the utility power supply and the building's electrical system. Article 230 covers the service entrance conductors, service disconnect, and grounding electrode system. It ensures that the service is properly sized and protected to provide a safe and reliable power supply to the building. NEC Article 250 covers grounding and bonding. This article provides requirements for grounding and bonding electrical systems to ensure safety and prevent electrical shock hazards. Grounding provides a path for fault current to flow back to the source, allowing the overcurrent protection device to trip and energize the circuit. Bonding connects all metal parts of the electrical system together to create a low impedance path for fault current. NEC Article 310 addresses conductors for general wiring. This article covers the requirements for conductors used in general wiring, including conductor types, ampacity, and installation methods. It specifies the allowable ampacity of conductors based on their size, insulation type, and installation conditions. It also covers the requirements for conductor identification, such as color coding and marking. NEC Article 314 covers outlet device, pole, and junction boxes, conduit bodies, fittings, and handhole enclosures. This article provides requirements for the installation of boxes and enclosures used to protect and support electrical wiring. It covers the types of boxes permitted for different applications, as well as the requirements for box fill and conductor support. It also addresses the installation of conduit bodies and fittings to ensure a complete and mechanically sound wiring system. These NEC articles provide a comprehensive set of requirements for the safe and proper installation of electrical panel boards and circuits. By following these guidelines, electrical professionals can ensure that electrical systems are installed in a manner that protects people and property from electrical hazards. Industry best practices often go beyond the minimum requirements of the NEC to further enhance safety and reliability. Firstly, load balancing. Distributing the electrical load evenly across all phases of the electrical system is essential. This prevents overloading any one phase and ensures efficient operation. Load balancing can be achieved by carefully planning the circuit layout and assigning loads to different phases. Secondly, surge protection. Installing surge protective devices at the service entrance and at panel boards is a crucial step in protecting electrical equipment from voltage surges. Surges can damage sensitive electronic equipment and cause fires. Surge protective devices divert excess voltage to ground, preventing it from reaching the equipment. Thirdly, arc fault circuit interrupters or FSIs. Using FSIs on branch circuits that serve receptacles in bedrooms, living rooms, and other areas where arc faults are likely to occur is an important safety measure. FSIs detect arc faults, which are a common cause of electrical fires, and quickly de-energize the circuit. Fourthly, ground fault circuit interrupters or GFCIs. Installing GFCIs in areas where water is present, such as bathrooms, kitchens, and outdoor locations, is essential for preventing electrical shock hazards. GFCIs detect ground faults, which occur when current leaks to ground, and quickly de-energize the circuit. Fifthly, proper labeling. Clearly labeling all circuits and equipment in the panel board is crucial for safe and efficient maintenance and troubleshooting. Labels should identify the circuit number, the area served, and the type of load. Sixthly, regular maintenance. Performing regular maintenance on electrical equipment, including panel boards, is essential for ensuring its continued safe and reliable operation. Maintenance should include inspecting connections, tightening loose terminals, and testing overcurrent protection devices. Seventhly, thermal scanning. Using thermal imaging to scan panel boards and other electrical equipment can help identify hotspots and potential problems before they lead to failures. Thermal scanning can detect loose connections, overloaded circuits, and other issues that may not be visible to the naked eye. Lastly, documentation. Maintaining accurate documentation of the electrical system, including panel board schedules, wiring diagrams, and equipment specifications, is essential for future maintenance and troubleshooting. Documentation should be kept up to date and readily accessible. Consider the historical context of electrical codes and practices. In the early days of electrical systems, there were few regulations and safety standards. This led to a high incidence of electrical fires and other hazards. As electrical technology advanced, the need for standardized codes and practices became increasingly apparent. The NEC was first published in 1897, and it has been updated regularly ever since to reflect the latest advancements in electrical technology and safety practices. Over the years, the NEC has become more comprehensive and stringent, reflecting a growing awareness of the importance of electrical safety. The historical changes in the NEC demonstrate a continuous effort to improve electrical safety and reduce the risk of electrical hazards. Understanding these historical changes can provide valuable insights into the current requirements and best practices. The physical layout and design of electrical panel boards are also important considerations. Firstly, panel board location. Panel boards should be located in a dry, well-ventilated area that is easily accessible for maintenance and troubleshooting. They should not be located in areas where they could be exposed to moisture, dust, or physical damage. Secondly, panel board size. The size of the panel board should be adequate to accommodate all of the circuits required for the building or facility. It is important to allow for future expansion when sizing the panel board. Thirdly, circuit breaker arrangement. Circuit breakers should be arranged in a logical and organized manner, with similar types of circuits grouped together. This makes it easier to identify and troubleshoot circuits. Fourthly, wiring methods. Wiring methods used to connect circuits to the panel board should comply with the NEC and industry best practices. Conductors should be properly supported and protected from physical damage. Fifthly, grounding and bonding. Grounding and bonding connections should be made in accordance with the NEC to ensure that the electrical system is properly grounded and bonded. Sixthly, labeling. All circuits and equipment in the panel board should be clearly labeled to identify the circuit number, the area served, and the type of load. Seventhly, accessibility. Panel boards should be readily accessible for maintenance and troubleshooting. There should be adequate clearance around the panel board to allow for safe and easy access. Lastly, environmental conditions. Panel boards should be protected from environmental conditions that could damage the equipment or create a safety hazard. This includes protecting panel boards from moisture, dust, and extreme temperatures. The importance of proper conductor sizing and overcurrent protection cannot be overstated. Firstly, conductor sizing. Conductors must be sized to carry the intended load without overheating. The NEC specifies the allowable ampacity of conductors based on their size, insulation type, and installation conditions. Secondly, overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors and equipment from overloads and short circuits. These devices must be sized to match the ampacity of the conductors they are protecting. Thirdly, coordination. Overcurrent protection devices must be coordinated to ensure that the device closest to the fault will trip first, minimizing the extent of the outage. Fourthly, selective coordination. Selective coordination is a design approach that ensures that only the overcurrent protection device closest to the fault will trip, while upstream devices remain closed. This minimizes the impact of a fault on the electrical system. Fifthly, arc flash hazard analysis. An arc flash hazard analysis should be performed to determine the potential arc flash hazard levels at different points in the electrical system. This information is used to select appropriate personal protective equipment for workers who may be exposed to arc flash hazards. Sixthly, short circuit studies. Short circuit studies are used to determine the magnitude of short circuit currents that could occur at different points in the electrical system. This information is used to select overcurrent protection devices with adequate interrupting ratings. Seventhly, voltage drop. Voltage drop must be considered when sizing conductors to ensure that the voltage at the load is within acceptable limits. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. Lastly, dirting factors. Dirting factors must be applied to conductor ampacity when conductors are installed in raceways or other confined spaces. This is because conductors in these environments are not able to dissipate heat as effectively. Proper grounding and bonding techniques are essential for electrical safety. Firstly, grounding electrode system. The grounding electrode system provides a path for fault current to flow back to the source, allowing the overcurrent protection device to trip and to energize the circuit. The grounding electrode system typically consists of a ground rod, a metal water pipe, or a concrete encased electrode. Secondly, equipment grounding conductor. The equipment grounding conductor connects the metal parts of electrical equipment to the grounding electrode system. This provides a low impedance path for fault current to flow back to the source. Thirdly, bonding. Bonding connects all metal parts of the electrical system together to create a low impedance path for fault current. This helps to prevent voltage differences between different metal parts, which could create a shock hazard. Fourthly, ground fault circuit interrupters or GFCIs. GFCIs are used to protect people from electrical shock hazards in areas where water is present. GFCIs detect ground faults and quickly de-energize the circuit. Fifthly, isolated ground receptacles. Isolated ground receptacles are used to reduce electrical noise in sensitive electronic equipment. These receptacles have a separate grounding conductor that is isolated from the normal equipment grounding conductor. Sixthly, surge protection. Surge protective devices divert excess voltage to ground, protecting electrical equipment from voltage surges. Seventhly, lightning protection. Lightning protection systems protect buildings from lightning strikes. These systems provide a path for lightning current to flow safely to ground. Lastly, testing. Grounding and bonding connections should be tested regularly to ensure that they are functioning properly. Testing can be performed using a ground resistance meter or other specialized equipment. When dealing with specific equipment and systems, consider lighting control systems. Lighting control systems can be used to reduce energy consumption and improve lighting quality. These systems can include dimmers, occupancy sensors, and time clocks. Also, emergency power systems. Emergency power systems provide backup power in the event of a power outage. These systems typically consist of a generator, an automatic transfer switch, and a battery backup system. Further consider fire alarm systems. Fire alarm systems detect fires and alert occupants. These systems typically consist of smoke detectors, heat detectors, and manual pull stations. Lastly, HVAC systems. HVAC systems provide heating, ventilation, and air conditioning. These systems can be a significant source of energy consumption, so it is important to design and operate them efficiently. Always consider energy efficiency and sustainability in electrical design. Firstly, energy-efficient lighting. Using energy-efficient lighting technologies, such as LED lighting, can significantly reduce energy consumption. Secondly, occupancy sensors. Occupancy sensors can be used to turn off lights in unoccupied areas, further reducing energy consumption. Thirdly, daylight harvesting. Daylight harvesting uses natural light to supplement or replace artificial lighting. This can reduce energy consumption and improve the quality of the lighting. Fourthly, energy-efficient equipment. Using energy-efficient electrical equipment such as motors, transformers, and appliances can reduce energy consumption and save money. Fifthly, power factor correction. Power factor correction can improve the efficiency of electrical systems by reducing the amount of reactive power. Sixthly, demand response. Demand response programs allow utilities to reduce energy consumption during peak periods by offering incentives to customers who reduce their load. Seventhly, renewable energy. Incorporating renewable energy sources, such as solar panels or wind turbines, can reduce reliance on fossil fuels and reduce carbon emissions. Lastly, building automation systems. Building automation systems can be used to control and monitor electrical systems, optimizing energy consumption and improving building performance. When performing maintenance and troubleshooting, safety precautions should be the top priority. Firstly, de-energize circuits. Always de-energize circuits before working on them. Verify that the circuit is de-energized using a voltage tester. Secondly, lockout tag out. Use lockout tag out procedures to prevent circuits from being accidentally re-energized while you are working on them. Thirdly, personal protective equipment. Where appropriate, personal protective equipment, such as safety glasses, gloves, and insulated tools. Fourthly, qualified personnel. Only qualified personnel should perform electrical work. Fifthly, proper tools. Use the proper tools for the job. Do not use damaged or defective tools. Sixthly, testing equipment. Use testing equipment to verify that circuits are properly grounded and that equipment is functioning properly. Seventhly, arc flash hazard analysis. Perform an arc flash hazard analysis before working on energized equipment. Lastly, emergency procedures. Be familiar with emergency procedures in case of an electrical accident. Specific troubleshooting techniques can be applied for common electrical problems. Firstly, voltage testing. Use a voltage tester to check for voltage at different points in the circuit. This can help you identify open circuits or voltage drops. Secondly, continuity testing. Use a continuity tester to check for continuity in the circuit. This can help you identify broken wires or loose connections. Thirdly, insulation resistance testing. Use an insulation resistance tester to check the insulation resistance of conductors. This can help you identify damaged insulation. Fourthly, ground resistance testing. Use a ground resistance meter to check the resistance of the grounding electrode system. This can help you identify problems with the grounding system. Fifthly, thermal imaging. Use thermal imaging to scan electrical equipment for hotspots. This can help you identify loose connections, overloaded circuits, or other problems. Sixthly, visual inspection. Perform a visual inspection of electrical equipment to look for signs of damage, such as cracked insulation, loose connections, or corrosion. Seventhly, circuit tracing. Use a circuit tracer to trace circuits and identify their connections. Lastly, load testing. Use a load tester to test the capacity of circuits and equipment. Consider the impact of technology advancements on electrical systems. Firstly, smart grids. Smart grids are using advanced technologies to improve the efficiency and reliability of electrical systems. Secondly, energy storage. Energy storage technologies, such as batteries, are becoming more affordable and are being used to store energy from renewable sources. Thirdly, electric vehicles. Electric vehicles are becoming more popular, and they are having a significant impact on the electrical grid. Fourthly, building automation systems. Building automation systems are becoming more sophisticated and are being used to control and monitor electrical systems. Fifthly, LED lighting. LED lighting is becoming more energy efficient and affordable, and it is replacing traditional lighting technologies. Sixthly, solar power. Solar power is becoming more affordable and is being used to generate electricity on a large scale. Seventhly, wind power. Wind power is becoming more efficient and is being used to generate electricity on a large scale. Lastly, advanced metering infrastructure, or AMI. AMI is being used to collect data on energy consumption and to provide customers with more information about their energy use.